What's up guys, I'm Sándor and this is Ubiton AI Labs. In this episode we are implementing a vector quantized variational autoencoder from scratch. So let's not waste time and get to work. This is the research paper that we are implementing today from 2017 from DeepMind, and we will also apply some optimizations on top of it. But what is vector quantization in case of autoencoders? Well, we have a convolutional neural network, which is our encoder, just like for the vanilla autoencoder and the VAE. It takes as input as an image, encodes it into latent space. But the change comes here because now we don't have a continuous probability distribution, like in the case of VAEs. We have a predefined sized codebook which stores the latent vectors. This means that if our codebook size is, for example, 1000, then we will only have at max 1000 tokens. Yes, tokens. Basically, the VQ-VAE tokenizes images into discrete tokens. And this makes it possible later on in other architectures to feed these discrete tokens into transformers. So now, just like ChatGPT uses the transformers for language modeling and prediction, we can tokenize images, feed it to transformers, and work with these images just like if they were words in language. So we will optimize basically this codebook such that it is used 100% or to a very high degree, and we will use these tokens, we will feed them into the decoder, and it will decode into an image. Now, don't expect stable diffusion like reconstruction quality, but it's a good starting point. It will be a simple example. And of course, in later episodes, we will also fine-tune it and get much better results. So we can open up a new Python notebook. As you can see, these are basically the libraries that we will use. I won't install them now because I already have them. And a few import lines. We need torch vision, of course, shorthand for NN and functional. And from the datasets library, we use load dataset because we are loading a dataset from Hugging Face. And a few others. We will use the torch built-in data loader as it's very handy. So let's load our dataset. And we will store it in data variable. And let's use the load dataset. Now the path is the repo name in Hugging Face. So in this case, I'm going to use the faces 128 dataset, which I converted from another high-resolution dataset. This is cropped and resized nicely. Feel free to use it. That will be our DS. It has a training and test split already made, and it contains only images, no labels. It only has an image column. And before we use it, we need to set a transform on it. That's gonna be, let's call it transform fn. We need to define that. So transform fn takes an example, actually multiple examples. And as I mentioned, our data set has an image column. So it's a columnar database, so this is multiple examples. We're going to call, let's make the name txf on E for E in X image, and we return X. Now txf is just a two tensor transform. I tried, and you could also try using a larger data set with larger images and try resizing them, cropping them here. The drawback is that the data loader will run these when the training runs, so it will slow down the training a lot. That's why it's better to either use pre-made data sets or make your own data set and upload it to Hugging Face with the transformations applied. I have a script for this uploaded to the Skool Community. It's free, feel free to download. It takes as input as a repository from Hugging Face, resizes the images into your desired format and uploads them into your account. Otherwise, you could map this data set and resize the images here, but it would also be, it would take longer time. So best is if you have a pre-made data set right on Hugging Face and you just load it and use it. Now we will have our train and test split and the data loaders for them. This is going to be ds train. Our batch size, we'll define that in a bit. We shuffle, of course, for training, and pin memory. Let's define batch size. And I'm not explaining everything in detail here. I did in the previous video, so just quickly implementing this. Feel free to watch the episodes about autoencoders, where I get into more detail about these parameters and functions. So now just return our train data loader, our test data loader, and the data sets as well. So this will be ds train, and we pick the image column. Like this. That's basically all of our data loading code. Pretty simple. It's done. Okay. Now we can start writing our encoder. It's a PyTorch module, of course, and we'll have a D argument. This is the dimensionality of the latent space. Define a forward function with x. Now just pass. And actually we can reuse this code. We will use it for our decoder and our vector quantizer as well. So this implements a convolutional neural network. We are working with 128 by 128 images, and we have a self.net, which is an nn.sequential model, so it goes layer by layer. Let's write an encoder block, input channels, output channels, and that's it. So we will stack these encoder blocks in the sequential, and the forward pass is just self.net, and we call it on X. Let's return a block. We perform a convolution with, of course, input channels. It will have number of output channels. The kernel size is 3, stride is 2, padding is 1. So we will downsample our image to half of its size. Now we can use a group normalization. I would say let's try putting that into an argument. So num groups, and the num channels here is output channels. Num groups, let's keep it at that. And now we should have a non-linearity, a ReLU, and perform it in place. Now additionally, you could add a dropout here. This isn't going to work. You could add the dropout here, but we will skip it for now. It should work fine just like it is. Now the asterisk I made here should come here. So we'll have an encoder block, and our input channels will be 5 actually, and I will tell you why later in a bit. So it's not just RGB, it's RGB plus 2 others. Output channels could be 64, num groups make it 16. So at this point we have a 64 by 64 image. We can do these a few more times. So 64 was the number of output channels, and that will be the same for the input channels here. We can bump up the number of channels to 128, so where we are now, that's 32 by 32 and 16 by 16. And let's not downscale much more. Let's actually bump this up to 256. And now in our previous implementations of the vanilla autoencoder, we basically did nn.flatten, and we had a linear layer to project it into a d-dimensional latent vector. Now, instead of doing this, we will have another conv2d layer with, of course, 256 input channels, and the output channels will be d, with a kernel size 3, a stride 1, and a padding 1. This means this will not downscale our image further, so we'll have 16 by 16. And the dimensionality will be d. Only that, the actual format of the tensor is d by 16 by 16, and of course when we have a batch size during training, then that. Now, what this actually means is that we are outputting a 16 by 16 grid of d-dimensional latent vectors into this latent space. And having a grid is great because it can keep some positional information about the input image. And that basically concludes our encoder. So now we can continue with our decoder. This will become decoder block. We can just copy this network and copy our forward pass as well. Now here it's going to be a bit different because we are upsampling the image with conv transpose 2D. We need a kernel size of 4 and the rest stays the same. And the encoder blocks become decoder blocks. And you should notice that the order is exactly the opposite, because this is decoding this many latent vectors to the original image. So let's just reorder these blocks. And from the number of input channels, we create 256. From 256, we reduce it to 128. From 128 to 64. And here, the output will have 3 channels, RGB, which comes here. So that keeps the size, and this makes it 32, from 32 to 64, and from 64 to 128. And here, let's just annotate this or call this variable as Z, or it's ZQ actually to keep the naming convention. I will explain this later. And now let's try if we were correct and test our encoder and decoder together and see if the sizes match. So let's pick an image from our trade data set. For example, the 200th image. So this will be a tensor. This will have this shape. 3 channels and height and width. Let's have our encoder with, for example, 64 latent dimensions, and the decoder also with 64 latent dimensions. Now we can run our encoder. Let's just move this to the device, because this runs on the CPU, and if we want to move it to our GPU, then we must define our device. In my case, it will be CUDA 1, my second GPU, and then we move both models to our CUDA device. Also, we can actually take this image here, move it to the device, and we can call our encoder to get our latent vector. Let's print its shape and maybe itself. Just need to run this code block as well. And we made a mistake. Which is that I forgot to put a comma here. So, num channels must be divisible by num groups. This is because in this last layer, our the number of output channels is 3, but we are trying to make a group normalizations on those channels. So let's take this last layer, customize it, and it had 64 input channels, 3 output channels. We don't need the normalization. Also, we will be using sigmoid because we are outputting values between 0 and 1. So as you can see, because we are expecting 5 input channels, but our image only has 3. So here's the trick. We will add positional embeddings to our input images. This will extend our X with 2 new layers, one for X coordinate and one for the Y coordinate. Maybe it's better to call in this case X as inp, since we are also working with coordinates. And here we can call X equals self dot add pos embedding on X. And we will call our network with that. We have a nice function called dodge.linspace, and it generates a sequence of numbers between start and end. So if we generate between -1 and 1, but how many steps? So let's take our input, which is a tensor of the shape batch size d, h, w. In this case, we can call D as C because this is an image. So these are the RGB channels, the height and the width, and it's multiple images, so we have a batch size parameter as well. So let's define a number called position X for each pixel. So if you take width number of numbers or steps in this linspace, then for each pixel you will get an X coordinate between -1 and 1. So 0 will be in the center. We need to have this on the same device. So we could also call imp.device, as both the encoder and the input will be on the same device. It doesn't really matter. And we will expand this sequence of numbers into the following shape. So this way, since our tensor has this shape, X will be repeated for all the rows from -1 to 1. And we will be able to attach it to our input with 3 channels. We can do the same for the Y coordinate, except we need h number of steps. But like this would also project -1, 1 range on the X coordinates. So we need to actually transpose this on the -2, -1 dimension. So this will be switched. So -1 will be on the top and 1 will be on the bottom. Actually, if we transpose this, then this will be swapped as well. And in our case, it doesn't matter really much because the height and the width is the same. But if they were different, this would be the exact way of writing it. Because then you transpose and the end result should be height and width and not width and height. So if we change these two, they will get back to height and width. So we have our two new layers with the coordinates, and we can concatenate our input px and py on dimension 1. This is 0 dimension 1. So this for the output will become 5. So let's rerun this code. We need to try the decoder as well. So we have a latent, and we can call our decoder with that latent. This we can call anything. And just print the shape of it. So yet our input image with 3 channels and this size gets converted into this 64 channel 16 by 16 latent grid of vectors. And if we feed them back to the decoder, we should get back our original image, except we will have a batch size as the 0th dimension as well. I printed too much, so let's not print these, only the shapes. And as we can see, it nicely converted back. So our encoder and decoder are compatible. So far, what we have now is basically a vanilla autoencoder, and the vector quantizer will be the heart of it. Let's leave it to the end and just quickly define our basic model class and our training code. So the VQ-VAE, of course, we will have the encoder and the decoder. We don't need to move it to the device because it will be automatically moved. And with the dimension, we just pass it. Here we have our encoder output. Here we will quantize it and decode our, for now, this is Z quantized, and just set it as ZE for now. So that's our result. So now we can get to declaring our model or some of our hyperparameters, like the learning rate. Our model itself is the VQ-VAE, and the D could be, for example, 256. We can define our optimizer, Adam W, the params, model.parameters, the learning rate is LR. Also, don't forget to move this to the device. Total epochs, set it to 0, and our min loss, just in case we want to save our model, should be the highest possible number. If we want, we can print out the number of parameters of our model which I usually do. And the number of parameters is defined as the sum of these. And usually we are talking millions. So let's divide this with 1e6 and with 2-digit precision. So currently our model has more than 2 million parameters. We will later adjust it, reduce it, or increase it as needed. So for the actual training code, before we start iterating over the epochs, I like to define an eval model function, set our model to evaluation mode, then in the end back to training mode. And we can use this decorator torch.inference mode, which replaces no-grad in this case. In some cases this is even faster, it performs more optimizations. So it's advised to use this, but you maybe need the latest torch version. So this evaluates our model on the test dataset. So let's pull X, our batch, from our data test field. Now here, since this model is pulled from Hugging Face and it has an image column, we need to map X to X image. And we can run our model on X. Just don't forget to move this to the device as well. And our model returns the reconstructed image. Maybe we should call it X hat. And our loss is L1 loss, not mean squared error, because the mean squared error loss tends to result in blurry reconstructions. So L1 loss, if you use that, it's gonna get a lot crispier. So the input is X hat and our target is X. Let's track the losses in an array. And when we finished running on the test dataset, we can create a losses tensor and take the average of it. Now, one key thing here is during training we should call detach, which we can also call here. It will make no difference because inference mode is on, so PyTorch will not track gradients and like that. So here just return our average loss. Now, before we train our model, I like to run this model evaluation just to see how good or bad the model's weights are initialized. And in this way I can compare the progress with basically complete randomness And then if the first log from the epoch comes in, I can see how it's converging even in the beginning. So the initial loss will be eval model, and we can print it just don't forget to format it nicely. So now we can iterate through actually I'm in range 1 epochs plus 1. So we need to define the number of epochs we want to train our model. Let's say that's 100. Notice that I put this into a different code block and not above, because this way we can run this block multiple times to train our model further, and it will keep the state of the model. So that's why I'm calling this local EP, so the local number of epochs, and we keep track of the total epochs here. So total epochs we manually increase, ensure that our model is in training mode. It's better to call this multiple times, just in case if you don't call it, it can lead to bad outcomes, let's say. So cool, we have this code already. We can reuse it. Here, except use the train dataset. And of course, we also need to optimize it and teach it, but now let's print out the average loss for this epoch. And we can say that epoch total epochs the training loss will be this, but we don't actually want to print this at every epoch. So if total epochs mod, say for example we print this every 5 epochs, equals 0, or local EP equals epochs, so at the end of this training loop we can evaluate our model as well. This will be EV loss. Okay, so what's left is actually teaching the model. So let's go here into the loop and let's set our optimizer gradients to 0. Set to none should be true. It's faster than setting everything to 0. So here is our loss. We can call loss.backward and optim.step. So one more thing, we should call this actually recon loss. Because this will only be the image reconstruction loss. We will have other losses later. And to make a placeholder here, let's just equate the final loss with recon loss. All right. Yep, I actually made an error here because of copy pasting. So this here and also this should be losses. So we're using a vanilla autoencoder, nothing crazy, with a latent dimensionality of 256, 2 million parameters, and we are training that with an L1 loss. Meanwhile, the training is running. Let's create a new code block. And I'm going to copy my utility functions here. This full notebook will be up in the Skool community, so you can download it and copy paste these functions for yourself. I don't want to live implement them because it's not really machine learning or AI related. It's just showing GIFs, saving GIFs, and showing images. So with this, we will want to see our original image and the reconstructed image and compare the two. And we can copy this code. But instead of a separate encoder and decoder, let's enable inference mode. Switch our model into evaluation mode as well. And this will be the reconstructed image. We can pick another image as well, as you see fit. So we can show the image using em_show img, and this will actually move it to the CPU and permute the channels so they can be shown using matplotlib. So the reconstructed image, we can show it like this, but it has a batch number as the first dimension. So because our model outputs images in batches, so if we squeeze it, then we will remove. This is the output shape from the model, and with squeeze we can remove the batch from the beginning. So our model is training, but it's close to a finish. As you can see, it's converging pretty nicely. I don't see any overfitting because the evaluation loss is actually better than the training loss. All right, so model training finished. I actually have a bit more epochs because previously I ran it for 5 or some, and losses were not the right variables here. So let's add our utility functions. And here is the reconstruction. So now let's destroy this quality with vector quantization. So we'll actually come here and make use of our not yet implemented vector quantizer. Let's call that self.vq. And the d is d, of course. However, yeah, let's put it here. We will have a k parameter here as well. This will be the number of codebook vectors that the quantizer stores. So we can extend our model as well with that parameter. And we can try maybe around 512 by 256. So that's 512 vectors of dimensionality 256 that we will store in our codebook. So instead of using this ZE that we basically right now feed into the decoder, we will pick a vector from this codebook of size 512 and use that in the decoder. So in order to have meaningful outputs, we will need to train the codebook itself and adjust the vectors themselves in the codebook. Self.vq on ZE. And now I will take it a bit slower and explain everything in more detail. So let's just assign self.d to d and self.k to k. And the vector quantizer doesn't take x, it takes ZE. So we have our codebook. We can create an nn.embedding. The number of embeddings is, of course, k, and the dimensionality is d. Now you could also use an nn.parameter, but my choice for now is the embedding. And we'll also have a self.beta parameter and just set it to 0.25 for now. So here it will get a little crazy. So I will comment the shapes here. So ZE comes in as batch size D, H, W. So what we actually need to do here is reorder the dimensions of this tensor to arrive at this shape. So we will have this many number of d-dimensional vectors. And as you can see, the codebook has k pieces of these vectors. So we need to calculate the distance from each of these vectors to these vectors. And we will pick the closest vector from the codebook and use that and return it as ZQ and use that in the decoder. Now we will need to employ some tricks because picking a vector from a codebook is not a differentiable operation. So we cannot train our network with that. Therefore, we will have a so-called ZQ straight through with a little trick. And a bit more other stuff as well. Easiest is let's define these so we can work with them. I just realized I've put on my headphones a while ago, but I'm so used to it to isolate the word that I didn't notice. So, getting back to here, let's reshape this vector. So take ZE, we will permute the dimensions. So the 0th dimension stays at the same place, that's batch. D is the first dimension of the tensor, so that doesn't stay there. We need H as the second one. We won't arrive immediately in this shape, but we need to put the dimensions in this order. So H is the second and W is the third dimension, and D is number 1. Now we need to realign how this is stored in memory in order to later view it. We could try this, but it's absolutely not guaranteed to work. Instead, it's almost guaranteed to break. So that's why we need to call this function. And D will be the last dimension, and the rest will be inferred as BHW. Cool. Now we have our encoder outputs organized into basically an array of D-dimensional vectors. Let's define E, which is the weight matrix of the codebook. It's just easier to use a single character than this long. And actually, Torch has a built-in function, cdist. So this calculates the Euclidean distance between vectors, but we are not going to use this because this actually calls a square root operation, which is computationally very heavy, and we don't actually need the distances. If we have the distances squared, that's also fine because we are only picking the closest codebook vector. So a bit of math. We have two vectors, A, for example, xy, and B, also xy. The distance is calculated, of course, first component-wise. You subtract bx minus ax and by minus ay. And for the distance, you square them, add them together, and take the square root of these. But we only want this part. And since we don't have named components, basically with tensors, we can do this. Now we will make use of the identity b minus a squared equals b squared minus 2ab plus a squared. Okay, to be completely precise, in case of vectors, because we need a number as the distance, so this AB can be calculated. First you take the length of vector B squared, the length of A squared, and mathematically if we transpose A and multiply it with B, this will become a dot product, and the result of it is a number. You multiply it by 2 and subtract it from these. So this is the term, and we need to calculate this. Now remember, we need to calculate the distances for each of these vectors. This is the number of the input vectors to each of the codebook vectors. So let me just move this below and we keep our nice math here. So the shape of this is now BHWD. The shape of this is KD. The shape that we want to arrive at, call it dists, is BHW and K. So for each input vector, we will store the distances to K codebook vectors. And from these K codebook vectors, we will pick the closest one to that particular input vector. So let's calculate first these two terms. So say Z2 Z multiplied, and so before continuing, let's open a new code block and create a quantizer with D3 and 4 codes in the code book. Now we would need a sample input, and in the shape batch size 1, RD was 3, and let it be 2 by 2 for height and width. Let's call it and print out the actual shapes. If you don't believe me, so Z E and Z2. So Z is 4, 3, that's K by D, but it just appears like that because this is height and width, it equals to 4. Let's make this 5 so we don't get confused. So this is batch size times height times width, which is 4 because we have a 1 batch size and 2 by 2 is 4, and we have the 3 latents. So we can be sure that at least this part works. Our codebook size is K by D, so we have 5 3-dimensional latent vectors in the codebook, and Z2 is 4 by 3, because Z is 4 by 3. Now, let's come back to this part and expand it. So if we have B with X and Y coordinates, then this will become, the length itself is square root bx times bx plus by times by, and this is squared. Therefore, we can just remove the square root and it will be this, or we can rewrite it as sum bi times bi for all I. So we have Z2 here, which is in the same shape. We need to sum each component. So let's do that. And we sum along dimension 1. So here. So we will have the Z squared for each 4 vectors in our input. Now we need this for, if we use this equation, then actually B is E and A is Z2. So we have this part. Let's do the same for E, E2. And print its shape. So now we see that Z2 is of size, it's actually 4 numbers, and E2 is 5 numbers. Now remember, the distances will need to be in this shape. So in this case, this is K. So if we just did and put a 1 here, and in this case we do keep dim true, so this is BHW and this is K. So we are kind of getting there, but we need this part. And the distances finally can be calculated. We have BHW Z2 minus 2 times, as the equation says, Z times ET, and in a bit I explain what this is, and let's go a bit deeper into this. So if we just take Z times ET, I were to call this hog, so Z times E transpose, let's print hog. So what's E transpose? It will become D by K. So now the vectors, the latent vectors, are in each row of this matrix. We transpose it, so the latent vectors will be in each column of that matrix. So ET has a shape of KD, and Z, as we saw, has a shape of BHW times D. Sorry, I miswrote it here, because if we transpose, that is the original, so this will be day key. Now this becomes a matrix multiplication, and the end shape will be BHWK. So what happens is that in Z we have this number of d-dimensional latents, and we transposed the codebook matrix. So each k piece of d-dimensional vector, as you write up the matrix multiplication, these will be the dot products. So each latent vector in this and in this will be dot producted, and the results will be written into this matrix. And this is the shape that we finally want, because for each input we will have k pieces of distances for each latent vector. And since Z2 is in this shape with the 1 in the end, this will mean that if I don't even write this here, that Z2, according to PyTorch's, or how PyTorch works, this dimension will be broadcasted across the k. And this dimension will be broadcasted across BHW, which makes sense because E2 is independent of the input latent vectors, the BHW number of latent vectors that come in from the encoder, and Z2 is independent from the codebook itself. So with this mathematical identity, we could rewrite our distance calculation without square root. And this will be actually distances squared, but I just write distances here. And the difference from this is that I wrote A as first here. So if we swap positions, then this will be identical. So we have now all these distances, and we need to find the closest vectors. So for each of the incoming vectors, we need to find the index in this k-long array where the value is the smallest. And for that we can use torch.argmin. The input is the distances, and on which dimension? Dimension 1. So among k. These will be our codes. So we have our code indexes actually, and let's comment these out. So this is in the shape of BHW, is the number of input vectors, and 1. This is in the shape of 1k. Therefore, this becomes BHWK, and I'm writing these here again. So this is BHW1. This part has a shape of BHWK, and this has a shape of 1k. What's the shape of codes? So we pick the minimum index for each BHW. It's going to be just BHW. Now to pick the quantized vectors, so that is the actual vectors from the codebook, we can take E codes. So this will index all the codes from this k number of the dimensional vectors. So this will pick the rows from that matrix. But the codes are BHW dimensional. So this will become BHW D. Note that these codes, one code can be the closest to multiple input vectors. So there are multiplicates in these codes. And this selection of latent code vectors will return, in some cases, or in almost every case, multiple codes. So one code multiple times even. So this will become BHWD. And cool, but torch.argmin is not a differentiable function. So backpropagation won't work with this. We need another way to come up with ZQ so we can return that and use for training. And that's what is called ZQ straight through, because the gradients can straight flow through it. And it's a simple trick that you take ZE and difference and detach it from the PyTorch compute graph. Now one thing is that we need to return ZQ straight through in this format. So we need to invert this operation. And ZE is in that shape and ZQ is in this shape. So this won't work as is. So let's just use, this is the simpler, more flatter shape. So let's use Z instead. And now we will invert this operation and return that ZQ straight through in this shape. So ZQST equals, now we need to view it as BHWD. So we just separate this first dimension into 3. Then we permute it. We permute this back. The batch is the first. Now comes D, that is index 3 here. Now comes H, that is index 1 here. And then W, the width, is index 2 here. And we need to realign the memory. So great, we can return ZQST. Let's try if this works or if I made any mistake. I did. And it's because I forgot to use the matrix multiplication operator here. So now we have it. Just don't forget to use the @ sign when you multiply matrices. Great. So this is a differentiable returned quantized vector, but that's not exactly everything that we need to do here. We pull up the research paper and to make sure the encoder commits to an embedding and its output does not grow, we add the commitment loss, the third term in equation 3. Thus, the total training objective becomes this. However, they talk about the third term. So this is called the commitment loss. This part is called the codebook loss. And SG here is stop gradient, so basically the detach function from PyTorch. And this is the reconstruction loss. It's our L1 loss that we already used in the vanilla autoencoder. So we need to return these two losses, and we will call this the VQ loss, and we will add this loss to the final loss during training. So this we define here. There is a codebook loss and a commitment loss, and both are defined using an MSL loss so the second distance squared, the Euclidean distance squared. And if we pull up again, ZA is the encoder output, and this is the embedding vector, so basically the vector from our codebook, which is ZQ. So in this case, we take ZE minus ZQ.detach. Just make sure that this line comes here. And in the other term, we stop grad on ZE. So basically this is ZE just permuted, reshaped into this form. And ZQST is in the same form. So we take Z.detach, ZQST. Now what this basically does is that during training, this one, during backpropagation, this one is treated as a constant, and ZQST will be adjusted. So the codebook loss actually moves the codebook vectors closer to the encoder's output. And the commitment loss treats the codebook vectors as constant and will penalize if the encoder outputs fall further away from this codebook. So it makes the encoder's outputs closer in this latent space to the codebook. Now the final VQ loss just this part, notice there is a beta here, which we set to 0.25. This means that we write it that the code book basically will move 4 times as fast closer to the encoder output. So we basically teaching the code book to move closer and closer to the encoder output, but we're also teaching the encoder to move closer to the code book at 1/4 of that speed. So they will approach each other, but if our beta is 0.25, then the code book will move 4 times faster towards the encoder output, which is the same as the encoder moves 4 times slower to the code book. And we return that VQ loss as well. All right, so we have our quantizer ready. So here we call it, but now it returns the VQ loss as well. So let's change this return value and let's call this x hat. Let's return x hat ZQ. This is the straight through actually. ZQ straight through and the VQ loss. Copy these 3 return values and let's go here in our evaluation code. And we have this loss, which is actually the reconstruction loss. We can add the VQ loss to arrive at the final loss. We don't need ZQ straight through here. Same way here in training, we have the recon loss and the final loss. We can add VQ loss to that. Now let's keep track of VQ loss as well. We can calculate the average here. And we can print it the same way. And we will see something very interesting during training. For now, change the epochs to only 1 and let's print down at the bottom, not at every 5 epochs, but at every epoch. So let's rewrite this 5 to a 1. And as you can see, the initial loss is 0 something, but by the end of epoch 1, the loss grows to this huge number, and most of it is the VQ loss. So if we were to train this for 2 epochs, let's just train it for 1 more epoch because the model keeps its state. So this time it was 20,000. Train for another epoch. Now the initial loss is 27, and now we have something like a million. So this is diverging, which means something is horribly wrong. And the loss here is growing every epoch because here we actually need to use the ZQ. and I tell you why. So ZQ straight through, when we take this part of the equation and detach it from the computational graph, this means that during backpropagation, the gradients only flow through Z, and Z comes from the encoder. So with ZQ straight through, when the gradients flow back from the decoder's output, ZQ straight through, they directly flow into the encoder and skip the quantization part. So using ZQ straight through will not be able to train our codebook. And ZQ is basically a part of the codebook with the selected codes. So if we use ZQ in this MSE loss, in both of these loss terms, and the final is the VQ loss, now we add the VQ loss to this final loss here. So when we do loss.backward, via the VQ loss here, it can immediately flow through back to the codebook loss and then to the codebook itself. And via ZQST, it will only flow through back to the encoder. So there is this split of the losses. One trains the codebook, this part, via ZQ, and the other trains the encoder via ZQST and then basically Z. So let's rerun this part of the code, reinitialize our model as well. Let's train for 2 epochs, and let's see now. As you can see, our losses are getting smaller, which means the model is converging. We have one more metric we need to keep track of, because we are always selecting the closest codes in the codebook, and these codes initially are kind of laid out randomly in that space. This will mean that for each encoder output there will be closest codes, and some codes will be used, but some codes might be dead and might never get used. So how do we keep track of what codes or how many codes are used? In this case, in our example, we have 500 codes, and the optimal usage would be around 80 or 90% at least. If we have many dead codes, then we will have strategies how to utilize the codebook more. But in order to do that, we have to be able to measure the codebook usage. And the way to do that is we create a one-hot encoding from the codes. Let's print what this does. So to align this a little bit better, so we can see, this means that this is the first code, second code, third code, fourth code, and the fifth code, because our codebook size is 5. So codes 0 in this array, for that encoder output, for the first encoder output, the closest code is the third one in the codebook. For the second encoder output, again the third code is the closest one. And it's the second code, and again the third code. So this means that in this case, this, and this, the first, the fourth and the fifth codes are not used at all in this simple case. So we would like to measure the percentage, basically, or the rate of this codebook use. And what we can do, since we created this one, hot encoding, is calculate the probabilities, which will basically we'll just do one hot dot mean on dimension 0 Of course, due to random, we will have a different matrix here. So if I copy this, we can see the probabilities that the first code was used 0% of the time, the second code was used 25% of the time, the third code was used 50% of the time, and so on. Now, from the probabilities, we can calculate the Shannon entropy, which is defined as and we can print that as well. Now, as you can see, this is not a number. And why that is because if we take the log of 0, that will not be a representable number, that will be minus infinite. So for these cases where a codebook is not used, we will just add a very, very small epsilon. And now we have an entropy. And the metric that we are after is called perplexity, which is just entropy exponentiated. So now we can remove these debug logs and return perplexity as well. And the perplexity will be a number between 0 and k. So the maximum perplexity is k. So let's keep track of this as well. And don't forget that we return this from the quantizer, like this. Let's return it from the model as well. Also in training. And the same way we add the perplexity and calculate the mean. Now I need a line break here around this, because it's getting too long. So perp, average perp, so as you can see, the perplexity initially is only 2. And then it even goes lower. Let's train it for 100 epochs. So now we are almost ready with the training, and as you can see, perplexity started around 2, And slowly it's growing. It's now 6, but our codebook size is more than 500. So as you can see, this is very slow. What we can do here is initialize our codebook better, so even in the end the perplexity starts from a very high number, and from then on it can learn much faster. Because perplexity is growing because our codebook is going closer and the encoder outputs are also. So the codebook is learning, but in a way too slow fashion. So what we can do is initialize our codebook with timing uniform. The tensor is self.codebook.weight. A stays at 0, mode fan in, and the non-linearity that we use is ReLU, because we have ReLUs in the encoder. So the outputs of the encoder will be distributed, shaped by the ReLU activation. So this should provide a better, or at least somewhat better, initialization. And to not log everything, let's change this to 5. I will rerun everything in my codebook. And let's see now. Quick fix, because I made a typo here. You might have noticed, because it's the research paper that we checked already shows it, but this should be a plus. So now I will retrain the network and show you the perplexities. So I commented out the timing uniform, so without codebook weight initialization, perplexity appears to stay a constant 1. This is the worst possible case. From all codebook vectors, every time only 1 gets used. So now I re-enabled the timing uniform init for ReLU. And now you can see the perplexity starts much higher and it continuously increases. But even after 50 epochs, we're only around 12% or so. So can we make this even better? And yes, we can. So instead, and we can comment this out, or we can keep it. It won't really matter so much. Instead of having let's say static in it with a uniform or some random numbers, we can actually initialize our codebook based on our training data. So take our model and let's write a function init codebook. We will accept a batch here, and from that batch we will sample the encoder, call the encoder forward pass on this batch, and we will initialize the codebook using these ZEs. Now ZE here is in the shape, well, a batch is batch size. We have D, H, and W. So we will need to reshape this first to the proper format, this one. So like this, And yes, we can extract these dimensions. But actually from here, ZE. So we will have BHW times T dimensional outputs from our currently untrained encoder, but even this provides a better distribution, an initial distribution, because the encoder starts to train from this. So if the codebook is initialized to what the encoder outputs in an untrained way, then gradually it's kind of like there, and it can pick up the vectors much more easily, and the codebook can be trained along with the encoder. So let's take self.vq, and we have our codebook. Wait. And we can copy these vectors. So that would be z up to self.vq.k. However, we need to ensure that this BHW term is greater than equal than k, otherwise we can't copy, or the codebook will have some empty values. Now, if you don't call this function, then that's why I said you can even keep this uniform in it. And here, let's assert that z.size0, that's BHW, is greater than equal self.vq.k. Let's run this. Reinitialize our model, and here, before the epochs, even before here, because when we train further we don't want to reinitialize, let's come to this block. We pick a batch from data train, we init the codebook with that batch. But we have to do this as well, in this case batch. So typo fixed here, it was batch x, and now we initialized our codebook. So we can see that even from this naive initialization that we took the first batch, the perplexity is a wee bit higher. So this is better than the coiming init, however far from ideal. Now, a better initialization would be to run a full epoch on the training set and store all the latents, or randomly fill, because this is memory intensive, so storing all the latents. So currently my model uses around 5.5 gigabytes of VRAM, and if I store the latents, it can easily go up to 10 plus. So you could store all the latents and randomly sample that data set and initialize the codebook from that. So I'm not going to live implement this now. Instead, I implement it and show you the difference. So I implemented an init codebook2 function, and instead of this batch, I passed the whole training data set. And naively, you would log all the latents, but I have 16 gigabytes of GPU memory, 32 with 2 cards, but logging the latents, it can take up lots of memory, so it's a really RAM heavy thing to do, and it doesn't really provide much better results. I saved the results from the previous training when we initialized it with the first batch, and as you can see, the perplexity is only very tiny bit slightly higher than previously. And why this is, and this isn't worth it, because it's really compute and RAM heavy for really slight gains. In some cases it might be worth it, but our training data set or data loader already shuffles the samples. So if you have a large enough batch size, then it should kind of, a few batches should kind of cover the whole training data set's distribution. Now, especially because I'm only using a faces data set, so the entropy is not so high because it's just faces, not cats, ships, mountains, and people and whatever. In this case, especially in this case, just sampling from the first batch, it provided almost the same results. I think that's basically all we can do with the initialization. However, there's another technique which is much less compute heavy and provides much better results. Instead of trying to initialize from the whole data set, let's revert and initialize from the first batch. And here we have, even after 50 epochs, more than 400 unused codes. So we could keep track of which codes are used and repeatedly, after some epochs, replace those dead codes with the outputs of the encoder. So for that, let's keep track of the codes. We register a buffer called codebook use. It's going to be a tensor of, actually let it be zeros, of size k and d-type torch.long. And here we have our codes for each batch forward pass. So if we are in training mode, let's count how many times each code is used. And we can refer to our codebook use like this. And it already knows it's a tensor. We can call the add function like this. So the code is an index in this codebook use. So the nth code, as many times as it is present in the codes array in this forward pass, will be added. Therefore, each index in this codebook use tensor represents that that code was used how many times. Of course, we want to reset this periodically when we refresh our codebook. Now let's go to the model itself and make use of what we already have. So we assumed that the codebook size must be smaller than the total latent vectors in a single batch. And we initialized all codebook weights using the first batch in the training data. So based on this, we can copy this function, rename it to refresh codebook. And I don't actually like accessing lower level data from the model itself, so we could wrap these functions and implement the same in the vector quantizer and just pass the parameters, but for simplicity and shortening the code, I will just directly access the codebook weights here. And so we store the codebook use in this variable. Now in refresh codebook, and this actually needs a torch.noGrad, before we change this, let's do the most important thing, that we need to zero the codebook use after we refresh. So we will take a batch and don't replace the whole codebook. We will only replace the dat codes. So we need to find the indexes of those codes where the codebook use is 0. And we can do that by take the codebook use, and if it's less than 1, and I will write it here instead. So for example, our codebook use looks like the first code was used 10 times in the last n epochs. This second code was used 0 times, this one 3 times, again 0 times, and 99 times, for example. This isn't a good codebook use pattern, but so this will be the codebook use. Let's make x equal and print x. So this will be true where the codebook use is 0. If we write non-zero, we will have 1 and 3 as indexes where it's 0. So actually, where this is non-zero, it's basically the true and the true if converted, and we can return it as a tuple. So in that case, this is a tuple here. The second element in the tuple is nothing, so can take the first one. Cool. Now we have a tensor, and we need to convert it to long, just to be sure, but I think even without that it will be a long, but just to be very, very sure. Okay, we can keep this sample code here or delete as you wish. And so basically this is the indexes of the dat codes in the codebook. So we already have lots of latents, And we can keep this assertion, but instead of k, actually we only need this len_dads for this function. However, we already assume that k is smaller or equal than VHW, so we can keep it at the same. So we have the indexes of the dad codes, which will be maximum, in our case, with the current parameters, 512. And VHW with 64 batch size is 16,000. So we could randomly sample as many as the number of dad codes and then copy there. So let's do that. So we sample up to VHW, but we keep only as many we need for the dad codes. So these will be the replacements. And now we can take this line, and instead of copying the full or replacing the full white matrix, we can address it with the dad code indexes and use replacements. And the codebook use will be zeroed out. Now this part, this is a hyperparameter, so you can adjust this. Maybe you want to replace codes that were used less than 5 times or 10 times. For now, let's stick to completely unused codes. So those completely unused codes will be called dad codes. So how do we refresh the codebook? So every 5 epochs we print. So I would go to the beginning of the epoch, and the same way as we initted our codebook, just paste this here, and if local EP, or you can go with total epochs as well, but when I retrain and if there are still dad codes, I like to replace it. What I mean is that if this equals 0, so every 5th epoch, refresh codebook, and this actually needs to be batch here, because I changed it back from init codebook 2 to init codebook 1, and that requires a batch. So this will be again batch here. And I like to do only when the local epochs are smaller than epochs times 2. And it's because this replacement is quite heavy. So after a while, if you replace many codes, I would just leave them a bit in the second half of the learning to by themselves try to converge. If it didn't work, since we wrote local epochs here, you can retrain it and it will again start to replace the dead codes. So here, why is taking the first batch sufficient? Because the training data loader has a shuffling on. This means that the first batch for every epoch, the data set will be completely shuffled. So the first batch will be completely different. Let's say random. So basically this is a random batch, and we refresh the codebook. With the encoder outputs of that random batch. One more thing, because I just set the indexes here. So we actually need to take the latents at these indexes. This way. Let's see if this works, and we store the previous results. Also, it would be useful to print that the codebook was refreshed, and useful to print the number of dead codes. And now let's fix any bugs. I'm expecting an error at the 5th epoch. Replaced 1 dead codes. No error, but not much replacement. Now it replaced almost 400 dead codes. And as you can see, the perplexity, remember this is average perplexity, it's much, much higher than ever before. Even at epoch 10, where we had 49, now it's 270, and it keeps replacing the dead codes up until epoch 25, so 5 times. 4 times. So perplexity is almost in the good area after 20 epochs. And you can also see that the training loss only after 20 epochs, if we compare, is much better than even after 50 the last time. So it replaced 4 times, and now it's just training. And as you can see, the perplexity, it still continues to grow, because the replaced codes are converging as well. Now the training for 50 epochs finished, and this training loss is made up of 2 terms, the VQ loss and the F1 loss. Now the F1 loss, this reconstruction loss, we can approximately know that a value of 0.03 and below 0.015 is a pretty good reconstruction. So where we stand now is for the total loss 582, and from that the VQ loss is almost half of it. So this is 3.3. I'm going to train this for 150 more epochs. That means for 75 epochs, this will keep replacing the codes. Now there's a big kind of turbulence when the codes are replaced. That's why for the rest of the epochs I leave it to converge smoothly. Okay, so my training finished. Let's analyze. So as we can see, the perplexity is slowly growing, and the training loss is increasing. Now this is not so terrible because the VQ loss is increasing as well, but if we take the difference between the two, the reconstruction loss is actually decreasing. At the end, it's below 0.03, just a little bit. Our evaluation loss is 0.06. We are not really overfitting, just a tiny little bit, but I wouldn't call that worrying. Now, our learning rate is pretty high. So I'm going to train this model further with a lowered learning rate. And in order to do that, I will have to reinitialize the optimizer. And let's train it with half of that learning rate for just 50 epochs. While this training is running, we can perform a small tweak here, because as you can see, many times the dead codes are 0. So you can either try and adjust this parameter to replace rarely used codes, but this so far is just working pretty fine. But if the length of the dead codes is 0, then we don't actually need to execute these. Okay, so this training finished. But we can see that the reconstruction loss, the difference between these two, went a little bit lower. Perplexity stays around 433. Now, remember we have more than 5,000, I believe, 5,300 something images in our training data set. And we are compressing all of them into 512 256 dimensional vectors. So this codebook contains the latents for all that data. And in this way, I wouldn't expect such a good reconstruction like this is the reconstruction from our normal autoencoder before we added the quantizer in. But okay, so it's a bit smudgier. But again, this is not a continuous latent pace. We only have 512 latent vectors. So I believe this is a pretty good reconstruction. We can further improve this by adjusting the hyperparameters, maybe more codebook vectors, but not sure. Maybe that could work better. We could even try decreasing the dimensionality and increasing the codebook vectors. However, there is something I would like to try, and that is normalizing the latent outputs of the encoder. So here, when we output the vectors into latent space, the last nonlinearity in this encoder block is a ReLU, and convolution doesn't normalize values, so the outputs of the encoder are not really normalized, because we have a group norm before. But what if we put a group norm here as well? Num groups and num channels. Now the output channels are D, and I'm going to peek a little. So this, to act as a layer norm, should be one group and the number of channels. That's the output number of channels. So I'm going to train this network with this setup for another kind of the same number of epochs. So first 200 epochs, or let it be just 150 epochs, and then another 50 epochs with half of the learning rate. So training finished with the group norm in, and it's around the same. It's a little bit worse. I would expect the same quality, kind of the same. So that didn't increase very much, but yeah, basically I think that's all, with one note in the end. Yeah, feel free to adjust the dimensions and play around with it. Also, the L1 loss in itself is not the best loss, because many research papers use adversarial loss and perceptual loss as well. So with L1 this is pretty okay. And one note is that you get back really smudgy reconstructions. It's probably because you downscale your image a lot. So I didn't even downscale it to 8x8, and if you were to downscale it to 4x4, there is no possible way with such a small bottleneck. That much information cannot flow through, so the encoder simply cannot reconstruct the image. So yeah, that's it. Thanks for watching.